Hello, here is another video on trigonometry. This is the first one, and we're going to talk about very basic ideas in trigonometry. So let us get started. Let me get rid of my picture here, we don't need it. So we're going to talk about, in your textbook, of course, that's chapter 5. In other textbooks, of course, it might be a different chapter, but the concepts that we're going to talk about are angles in general, and unit circle, which is the foundation of the modern trigonometry. We're going to talk about the 6 trigonometric ratios and do some application of it, and we continue in other chapters, but let's get started. So in mathematics, a function that repeats its values in regular intervals is known as a periodic function. And what we want to do in this chapter is really investigate different types of periodic functions. And the 6 trigonometric functions are periodic. So let's start by a very basic idea, and that is an angle. Now, you know from geometry what a ray is, right? A ray consists of one point on a line and all points extending in one direction from that point. Now, you don't have to, sweat too much on that definition. Just think of ray. You know what a ray is. It has one end point and the other direction goes forever. That's a ray. And the way you name rays is by using let me get a pen so I can write on this. So we use this notation here. So the first letter is the end point, and the other letter is some point somewhere on that line, right? So EF, ray EF, you could just put a little arrow on the top like this. That's ray EF. Okay. Now, if two rays intersect at their end point, then we have an angle. So this is an angle right here. As you see, the way we name angles is by writing 2 points on 2 rays and one at the point of intersection, which we call the vertex of the angle. So you can call an angle DEF, or you can also call it FED if you want to, as long as the vertex is in the middle. And then there is a symbol for angle. That's angle FED or angle DEF, right? All right, so that's an angle. That's basically what an angle is. So angles can be named using a point on each ray and the vertex. Now, letters that we use to represent angles are the Greek letters theta, phi, alpha, beta, and gamma. So we start 2 rays. These are lying on the top of one another. So we start with two rays like this. So one of them is here, the other one is on the top here. And then we move that one of them, we keep it here. That's got the initial side. And the other one we rotate it either this way or the other way. We're going to talk about that. But for now, let's say counterclockwise. We rotate it and make an angle, right? So that's the terminal side right here. And that one that we keep fixed is the initial side. And of course, this is the vertex of the angle. All right. So we have to find some kind of unit to measure angles. Now, right away, the way that we define an angle, there is a problem, because if you think of the angle that 2 rays make, well, there are 2 angles. There is this one, and there is also this big one, right? So which one are we talking about? Well, that's why we have to talk about oriented angles. So we're going to remedy that in a moment. Okay. So this is the angle, and we can talk about oriented angles in a second. So angles and their measures. Now, one measure of an angle is basically to think about, if you go all the way, rotate all the way around completely, what should we call that? And then we can call the smaller angles part of that. So historically, Babylonians divided this one rotation into 360 parts, and because their number system was based on 60, we count to 1, 2, 3, 4, 5, 6, 7, 8, 9. When we get to 10, then we group them. So what they did, they counted all the way to 59, and then 60. When we got to 60, they grouped them. So their number system, place value kind of system, was based on 60. That's why we have 360. All right. So that's the idea from Babylonians, and we have that they divided this one rotation to 360. So 1 out of 360 is called 1 degree. So it's kind of a small 1 degree, but you can imagine, an angle that has a measure even smaller than 1 degree, right? So what they did, there was 1 degree, and then divided 1 degree into 60 parts, and that was a minute. So 1 degree was 60 minutes, and then divided each minute into 60 parts, and that was second. So each minute is 60 seconds. Just like we divide the hour and a minute and seconds with time, that's what they did with degrees. All right, so now we're going to talk about oriented angles. So if you fix one side, initial side, and you move the other side, we call the other side terminal side. And if you do it counterclockwise, then the angle is positive. If you do it clockwise, then the angle is negative. That's just by definition. So this way we have orientation. So each direction has, its own definition. All right. So clockwise is positive, is negative. Counterclockwise is positive. Okay. So an angle is said to be in a standard position if its vertex is at the origin and its initial side coincide with the positive x-axis, as you see here. So this would be the vertex of the angle. This is always the initial side, and then the terminal side rotates to make an angle. If that's the case, then this angle right here is in standard position, because you can have angles everywhere. You see how difficult it is to compare them and work with them because they're everywhere, right? If you take all of them and put them in one place, then we can actually work with them in a more organized way. So that's the standard position of an angle. The initial side is at the positive x-axis. The vertex is at the origin, and the terminal side makes either positive angle or negative angle. If you go the other way, you make negative angle. If you go counterclockwise, you make positive angle. All right. So now angles don't have to be from 0 to 360 degrees. It could be they could be bigger. For example, if you notice here, this angle right here is 0. This angle is 90 degrees because it's 1/4, right, of 360. So that's 90. This one is 180 because it's half of 360, right? And this one is 270, so it's 1, 2, 3/4 of 360. And so what about this one right here? Well, this one, since we're going counterclockwise, you see, if you're going counterclockwise, it's positive, so that's 360 plus another 90, so that's what? That's 450. So we can have angles that are greater than, of course, 360. Now here in the notes, if you click over here, you can open up a let me leave page here. See right here, I can make an angle when it's ready. Here you go. So you see, I can make an angle like that, and that angle, of course, is getting bigger and bigger and bigger and bigger. Now this is 360. We passed 360. Now it's 500 something. As you see, we can have any angle, any size, right? And would be a positive angle. And we could also let me go over here. All right, could also do it the other way around. Could also do it this way. And this one, these are negative angles. So let me, it's still working on it. There you go. So you see, this is negative angle going the other way around and making negative angles. A negative angle could be a bigger, in absolute value, bigger than 360. See, that's 360, and then this is negative 400 something. See that? So angles could be bigger than 360 degrees. Now, two angles in standard position are called coterminal if they share the same terminal side. For example, here, this angle has that terminal side, and the angle that starts from here and is negative and goes this way also has the same terminal side. So these two angles, 120 degrees and negative 240 degrees, are called coterminal angle. There is a extra n there, forget about that. Coterminal angle, not conterminal. Coterminal angle. So they share a terminal side. Coterminal, that's how you spell it. Two coterminal angles are basically angles that have the same terminal side, right? Now, if you notice, if we have an angle alpha, and we want an angle that is coterminal to it, we can easily create that by adding 360 to it. So if I have, let's say, 120, if I want a coterminal angle, I can say, okay, I'm going to go this way one time, 360, and then come over here. So it's 360 plus 120, that's 480. So 480 is coterminal to 120. I could also go the other way around. I can also go this way, say, okay, I'm going to go this way, right? One complete turn, right? And then go that way, 120. That means I want to subtract 360 from it. Or you can say add negative 360 to it. So that means we can put a k here. K is an integer, so we can add multiples of 360 or subtract multiples of 360 from the angle to get another angle that is coterminal to it. That means we can find infinite number of angles that are coterminal to a given angle, right? All you have to do is let k be an integer. K be 0, be 1, negative 1, 2, negative 2, and so forth, and you can find different angles that are coterminal to angle A. Okay, so here is an example. Graph each of these um, angles. These are oriented angles, right? Oriented angles in a standard position and classify them according to where their terminal side lies. Now, if we have, of course, in a standard position, we have the coordinate planes, right? Coordinates plane. Now, if an angle, terminal side of an angle, ends up in the first quadrant, then that's the first quadrant angle. If it ends up in the second quadrant, it's called second quadrant angle. And in the third quadrant, it would be a third quadrant angle. If it's in the fourth, it's a fourth quadrant angle. Now, if the terminal side ends up here, for example, on the axis, on one of these axes, then they're called quadrantal angles. They're not in any quadrant, but they're quadrantal. So they're kind of on the axes. Like 90 degrees, for example, is a quadrantal angle. Okay? So let me erase all that. So the graph of this 60 degrees is right here because it's positive, it's counterclockwise, right? Negative 225, we have to start from here. This is 180. How much more I have to go? 245 more. So it's going to be right there, right? So that's the terminal side. That's what it is. Negative 225. All right, it says find three angles that are coterminal with each angle. Well, first of all, 540, right, is positive, so I have to go this way. That's 360. How much more do I have to go to get to 540? Well, 180 more, right? So 540 is this angle. Now, if you want a coterminal angle to that, all you have to do is just add what? Add 360 to it. I did that here on the calculator. So 900 is another angle that ends up exactly in this place. 900 degrees. And now I can also subtract 360 from it. So 540 minus 360, that means I go the other way, a negative side, right? 360. That's 360. And then we can go this way, 180. So that's another coterminal angle. Or I can add two negative 360s to it, or subtract 360 twice, and I get negative 180. Negative 180 is right here. That's coterminal too. So you can easily find all the coterminal angles to 540. You do the same thing for the other one yourself. Okay? Do exactly what I did. Yeah, you can use a calculator. All right. So what is radian measure? Well, dividing one rotation into 360 has really nothing to do with the circle and what we are doing here. Just somebody decided to divide it into 360. If you lived in Babylonia maybe at the time, if you decided to divide it into 400, we would be working with 1 over 400 of a circle. So it's arbitrary. If somebody decided to do it, has nothing to do with the circle and rotation. But we can come up with a measure that has to do with rotation actually. And that is called radian. What is it? Well, you know, and people have known this for centuries, that if you take a circle and take the circumference of a circle and divide it by the radius of the circle, you're going to get 2 pi. Now, if you divide, instead of by radius, if you divide by diameter is 2 radii, right? So that's the diameter. If you divide by diameter, you get this interesting number, pi. And people have known this for a long time. And pi is about 3 point something, right? So we know that the circumference of a circle, the formula for it is 2 pi times the radius, right? So that means in one circumference there is this many radii. And the radii, I mean the plural of radius. So that means if you measure the radius here, let's say it's this much, and if you take that and put it over the circle circumference, so that's one radius, and then you can make another radius here on the circle, is another radius, and then another radius, and so forth, right? So if you do that, we can actually say that the angle that we make here, such that the length of the arc from here to here equals to the radius. If this equals to r, then we call that angle 1 radian. And as people have known this for a long time, one circumference, one complete rotation has how many radii in it? 2 pi. 2 pi is like through 6.28, right? That means there are 6.28 of these radii in one complete turn, right? So that's what the picture looks like. So no matter, and this is true, no matter what the size of the circle is, whether it's a small or it's big or huge or whatever it is, this relationship is still the same. That there are what? That there are 6 of these, 6.28 of these in one rotation, in one circumference, no matter how big or small the circle is. All right? So, so that means if I want the whole circumference, the formula is 2 pi times radius, and 2 pi is how many radian is one complete turn, right? One complete turn is 2 pi. So if I want to find the distance all the way around here, right? All I have to do is take this 2 pi radian, now that we know what it is, it's 2 pi radian, and multiply it by the radius. What if I only want this part? Only s? Well, by the same formula, s has to be whatever the angle is in radian, whatever this angle is, theta in radian, times radius, right? So now we found the formula to find the arc length for a circle of radius r. And that arc length, when r, right, when r is the same as s, right? Theta, of course, from here, you can say theta is s over r, right? And if the arc length and the radius are the same, what do we get? We get 1. So we call that angle 1 radian, the measure of it. So that's the definition of radian. So one complete turn has how many radian in it? 2 pi, which is 6.28, right? So if you think about, for example, 45 degrees, we know that 45 degrees divide the, let's say, think of a pizza here, vegetarian pizza. It is divided into 1, 2, 3, 4, 5, 6, 7, 8 pieces, right? So if you cut the slices with 45 degrees, you get 8 equal pieces. So each piece is what? Each of them is going to be 1/8 of the complete, not this, but I meant the size of it, this one, the arc length for the piece, not the whole area. We're going to get to the area in a second. So this part right here, right, this they got two circles. There's a small circle and there is a larger circle. For the small circle with radius 2, this is going to be the angle in radian. Now 45 degrees in radian is 1/8 of the whole thing. So 2 pi, think of 1/8 of 2 pi, that would be what? Pi over 4, right? So in radian, 45 degrees is pi over 4, right? Now, also, you can say, okay, for the smaller circle, that would be pi over 4. And for the larger circle, it'll also be pi over 4, right? Because it's 1/8 of what? 1/8 of the whole, one turn, right? Now, of course, we have to, this is true if we have radius equal to 1, but the radius is not 1. So let's look at it here. For a smaller circle, the radius is 2. So this S here, this distance from here to here, that right there, let me clean this up. So this right here for a small circle, right, is what? Is 1/8 of the circumference of this circle, the small circle. Circumference of a circle, the small circle would be 2 times 2 pi, right? The radius is 2, 2 times 2 pi is 4 pi. So 1/8 of 4 pi is pi over 2, right? So, so S, this S right here for the smallest circle is pi over 2. Now, what about S for the bigger circle, for that one? Well, S is going to be 1/8 of the circumference here. And the circumference there is 6 pi because 3 times 2 pi. So that's the circumference of the big one. And 1/8 of it is 3 pi over 4. So this one is 3 pi over 4, the length of it. And the S right here is pi over 2. Now, pi is 3.14 divided by 2 is like 1 point something. This one is 3 times 3 something. It's like 10 something divided by 4. That's the length right here. But also, we realize here that is the same as what? That's the same as multiplying the radius 2 by the angle pi over 4. That's what we get if we do that. So that's another way to prove the formula for arc length, which is what? R equals to, S equals to R times theta, which is right here. It is true in both cases. No matter how big the circle is or how small the circle is, that formula is always true, right? The arc length is radius times the angle, but it has to be in radian, right? All right. So it says the circumference of a circle is 2 pi r, we know that. So there are 2 pi radians in one complete turn, which is approximately 6.28 radii, radius lengths, right, in one turn. Now, that means 2 pi radians is the same as 360 degrees. So if you divide both sides by 2, we get pi is 180 degrees. So pi radian is 180 degrees. And if you divide by pi here on both sides, you see that pi over pi is 1. So 1 radian is about 180 divided by 3.14 is about 57.3 degrees. So 1 radian is about this much, and that's about 57.3 degrees. Now, if you want to divide by 180, then the right-hand side would be degree, so that would be 1 degree. So 1 degree is going to equal to this much radian. That means 3.14 divided by 180, which is this small number. So 1 degree, which is kind of hard to actually draw, but let's say 1 degree is really, really small. 1 degree is this much radian, 0.017 radian. It's a very small number. So if you want to convert from degree to radian, you just multiply by pi over 180. If you want to convert from radian to degree, you multiply by 180 over pi. The way you remember this, if you want to go to radian, the numerator has to be pi, radian. If you want to go to degrees, then the numerator has to be degrees. And you can easily apply this formula. For example, convert each radian measure to degrees. What's pi over 6 radian? So we multiply by 180 over pi. The pi's go away, so we get 30 degrees. And what is 3 radians? 3 radians is about 172 degrees. Why? Because you can multiply by 180 over pi. You can do that with calculator. Okay? Convert 15 degrees to radians. Well, 15 and then to radians, you have to multiply by that. You can write it in exact form, or if you have a calculator, you can write it in decimal form. All right? All right. So I think I repeated that over here for no reason. We can ignore that. Okay? That's how we convert. All right. So finding coterminal angles. If two angles in a standard position have the same terminal side, we said that there are coterminal angles. So if you're given an angle, let's say 140, you can actually, or if you're given 220, doesn't matter which one. Let's say you're given this, and you want to find the coterminal angle. Well, you use this formula. Just keep adding or subtracting multiples of 360 to get coterminal angles. That is in degrees, right? You can also do that in radian. Now, how many? So it says find the least positive angle that is coterminal with an angle 800 degrees. Okay, so we want a smaller angle from 0 to 360 that is coterminal to that. So the way we do that is we say, okay, how many 360s are in 800? We know there are 2 360s in 800, and that's 720. So we take that away from it, and we get 80. Because we were told to find a small angle, so this is a big positive angle. Obviously, you have to take away 360 from it until you get to what? Something that's smaller than 360. And you're done. All right? You do that with the calculator, right? Divide whatever angle you're given by 360, you get a number. Pick the whole part of it, multiply that by 360, and take away that from the number, right? So you don't have to worry about the decimal part, just the whole part. How many 360, whole 360s are in 800? 2. All right. So in radian, in degrees, to find the coterminal angle, the formula is that. In radian, the formula is this, of course. You keep adding and subtracting multiples of 2 pi, because 2 pi is 360 degrees. All right? So here it says show the angle with measure negative 45 on a circle and find a positive coterminal angle alpha such that alpha is between 0 and 360. So in degrees, the way you do it, we want an angle, of course, positive angles. So this is a negative angle. So we have to add 360 to it. So we just have to add one 360 to find the angle 315. If you want to do this in radian, we have to think of negative 45 as in radian would be negative pi over 4. And add 2 pi to it. Give a denominator of 1 here, then make the denominators the same. Multiply by 4 here. So we have negative 1 pi over 4 plus 8 pi over 4 is 7 pi over 4. That's coterminal in radian. All right? That's how we find coterminal angles. Now, you can find more, just add or subtract multiples of 360 or 2 pi. All right, finding the length of an arc. Well, we know the formula to find the length of an arc is theta times r, right? So if we have a circle and we want to find that part of it, let's say from here to here, that's S, and we have r and we have theta, that's the formula. Now think of the, it says in 1 Earth day, Mercury completes this much of its total revolution. So Mercury goes, we assume is a circle, is not, is actually ellipse, but let's assume is a circle. So this is the Mercury. So in 1 Earth day, Mercury completes this much of its total revolution, right? How many? So this is actually rotating by itself, right? So Earth goes around it in 1 Earth day, right? Rotates one time, that's 1 day. Mercury in 1 Earth day goes only this much of its rotation, finishes this much of its rotation, right? That's not going around the sun, it's actually rotating, right? So how many miles does it travel in 1 day? So use your answer from part A to determine the radian measure for Mercury's movement in 1 Earth day. So we know Mercury's orbit, so the Earth day is when the planet Earth rotates one time, right? But the Mercury goes around the sun here, right? We assume is a circle. And how much of this 1 day on planet Earth passes, 1 day passes, how much of this orbit does Mercury actually travel? That's the question. So all we have to know is this theta in radian and this radius. So what is the circumference? It says Mercury's orbit, since we know that somewhere over here, so it says C is 200, Mercury's orbit is, right here we are given 36 million. It says Mercury is approximately 36 million miles from the sun, right? So we assume that the radius of rotation revolving around the sun is about 36 million right here. So 36 million times 2 pi radius, that's the circumference of this is the whole thing. So C is approximately that many million miles. So Mercury completes this much of this whole thing. What is the S for this much of the path? Well, we know that the whole thing, the circumference is this much. So the question is, what is this much of that? And we multiply, right? And we get about this many million miles. So that is S right here, right? So what we want to find, it says use your answer from part A to determine the radian measure for Mercury's movement in 1 day, 1 Earth day. So what is that radian measure? What's that angle, right? And to find that angle, we use the relationship between theta, S, and R. So theta is going to be this number, which is S that we found, divided by radius of the Mercury, which is 36 million miles, not that. It's an extra 3 there. I have to fix that. Okay, so divided by 36 is about this many radian, right? The millions go away. So it's 2.58 divided by 36. That's what that is. All right. We just found a few typos there too. Finding the area of a sector. Now, so if you have a circle and you want to find the arc length from here to here, all you have to do is take theta, in radian, and multiply it by radius. Now, it turns out that if you have, let's say, a pizza, and you want to find the area of this slice, well, the area of that slice, let's call it A, and R, and that angle theta, so this angle right here is theta, the relationship between them is this right here, which is similar to the relationship for the area of a circle. What's the area of a complete pizza? Well, the area is going to be, remember the area of a circle, pi r squared, right? Now, it looks like if you want the whole thing, all we have to do is take the angle, which is 2 pi, divided by 2, you get pi, and multiply by radius squared. So if you follow the same formula, then the area for that piece, right, is going to be half of the angle times r squared. And that's exactly what we have here, right? Now, another way to prove this formula is to think of the circumference of a circle divided, right? So let's say this is circumference of a circle and this is S. So this is the circumference, this is S. Now, S divided by circumference has to be the same as the area of this slice, which is A, divided by the area of the whole circle, right? And that's exactly what we have here, see? And if you simplify this and solve for A, then that's what you're going to get. You get this formula. Because we know S is what? S is actually R times theta. So if you substitute that and isolate A, we can prove the formula. Okay? All right. So we have a formula to find the area of a slice of a pizza. We call it a sector, right? So to find area of a sector, make sure you take the angle, convert it to radian, right? Convert to radian. 30 degrees is pi over 6. And then take half of that, half of pi over 6, and multiply it by radius, which is 20 squared. So it's about that much. Squared. This is foot squared, right? So now you have to know the radian measure of famous angles. 360, of course, is 2 pi. 180 is pi. 90 is pi over 2. 60 is pi over 3. Just think of pi as 180. And 45 is pi over 4, which is 180 divided by 4. 30 is pi over 6, which is 180 divided by 6, right? So you should know these without really trying to convert. All right, now in rotational movement, think of an object moving in a circular path. Well, the object, as it moves, if you think of it as being at the end of the terminal side, as it moves, it makes angles. It makes an angle, and also it creates S, which is the arc length. So it has two kinds of velocity. The velocity going on a circle is basically similar to the velocity of going with the car straight, right? You just take the distance that it goes and divide it by time. So that's called the average linear velocity of the object. Average because we assume that it doesn't change as soon as the object starts moving. It goes with the. It makes it easier here to think of velocity as being constant, so it doesn't change as the object goes around. It remains as, let's say 20 feet per second, linear velocity. So the average of it is s over t. Now, there is another type of velocity, and that's called angular velocity. Angular velocity is how much angle it makes per unit of time. How much angle in radian divided by unit of time. And that's angular velocity, or omega. So we have omega, which is angular velocity, is the angle how much angle it makes divided by time, how much time. And then we have linear velocity, which is s divided by t. Now we know that s is actually r times theta, right? Now if you substitute for s here, r times theta, it looks like the linear velocity is r theta over t. But we know that theta over t is actually omega. So linear velocity of an object moving in a circular path is given by r times omega. So if you know, for example, the wheel's radius, and you know how many turns it goes around, you can multiply and find the linear velocity of a point on it. And if you think of this point as the point that is touching the ground, then the linear velocity of that point is the same as the linear velocity of the wheel moving straight, right? Because the distance that this point touches on the ground is the same as the distance, s, right? So if the wheel goes that way, right, this point, then if this point touches, then this point touches the ground, then this point touches the ground. So it looks like linear velocity, this distance that the car goes, is the same as this arc length. And the velocity, linear velocity of it is the same. They're the same. That velocity and this velocity are the same. So it looks like we found a really good application of this, right? So let's look at, this is San Jacinto College, on the Spencer Highway in Pasadena, Texas. And we know that the San Jacinto College latitude is 29.6911 degrees north. Usually the latitude are given in degrees rate, minutes and seconds. I just converted it here to just, decimal. So that is the angle, right, that it makes here, that angle right there. So not that angle, but from the north. So is right 29, about 30 degrees north, right? So now at this point, think of this circle that San Jacinto, when the Earth moves this way, San Jacinto, every point on the Earth also is moving. So you can think of the college moving on a circular path like this. And we know the radius of this path is 39 miles. So the question is how fast the college actually is moving with the Earth. How fast is it moving? Well, that's a linear velocity, right? And that's just what? That's omega times the radius. We know the radius, we have to find the omega. Now, what is omega for the planet? Well, we know the planet goes around one time in 24 hours, right? So omega is 2 pi radian, one complete turn. How long does it take it to do that? 24 hours. So the linear velocity of the planet Earth is pi over 12, right? Pi over 12. That's how fast it goes, right? Linear velocity. And the unit is hour. So pi over 12 is, you divide 180 by 12, what do you get? You get about, 15 degrees, maybe. So 15 degrees per hour. In 24 hours, you get, 360 degrees. Okay, so the linear velocity is r omega, and multiply 900 miles per hour. Next time you get a speeding ticket on that Spencer Highway, tell the cop to add that velocity to your ticket, because if you're going east. All right, so I'm going to end this video here, and we're going to continue in the next video and talking about unit circle. We talked about basic ideas in trigonometry, in angles, and so now I'm going to come back here and say bye to you, and I see you in the next video. Okay.